Hello everyone. In this video we are going to talk about the phase space of a simple harmonic oscillator. So what is a phase space? Well, a phase space is a space in which all the states of the system are represented by using some points in this phase space. So say for example we have a system which contains a simple harmonic oscillator. So all the states of this simple harmonic oscillator can be represented by some unique points in this phase space. Now, what is this phase space consists of? Well, phase space is a space which consists of the variables which completely specify the state of the system. In classical mechanics, we need two variables in order to specify a system. Now, why two variables and what are these two variables? This is because Newton's second law, which is F equal ma, is actually a second order differential equation in time. That is, it is mass time the second derivative of the position with respect to time. Now, in order to find a solution for this equation, you have to integrate it twice, right? Those integrations will give you two constant of integrations. Now, in order to specify a unique solution, you have to specify those two constants of integrations. That's why we need two variables to completely specify the state of a system in classical mechanics. Well, what those two constants of integration are? Well, let's find out. Okay, so you see, from here we can write down that the second derivative is actually f over m, which is actually the acceleration a. So if you integrate it with respect to time, you should get d dt of x, which will be equal to a t. Okay, you have to integrate this thing. So if this is not constant, so you'll have to integrate it like this, plus a constant of integration. Let's call it c1. Now, as you can see, this one, c1 is actually a velocity, right? Because this is a velocity. Okay, so one constant of integration is velocity. And what is this velocity? Well, you'll see this is just the initial velocity. Now, if you integrate it again, what you have is x will be equal to, you integrate this quantity again, so an integration of this thing, okay, plus c1 with respect to time, plus another constant of integration. And as you can see, this constant of integration is actually another position, and if you put the appropriate limits, you will see that this constant of integration is actually the initial position. So the two variables that specify the system in classical mechanics are position and velocity. And sometimes in classical mechanics we use momentum instead of velocity. So the phase space in classical mechanics is a space of position and velocity or momentum. Okay, so if we represent position by using this axis, okay, and velocity by using this axis, then this is the phase space in classical mechanics. So specifying any point on this space actually means specifying the initial position or velocity. Well, it can be initial or it can be the position and velocity at any time, okay? Now, if we know all the position and velocities of the particle that we are considering over time, we can draw a curve in this space which will represent the motion of that particle in phase space. That is, in real space or the physical space, the particle will move from one point to another with some position and velocity, okay? And here we plot those positions and velocity and we get another curve. We call that curve the phase space trajectory of that motion. Now, right at the beginning, let us clear some concepts regarding phase space. So, in a phase space, can we have a trajectory like this? Well, actually, we can have this trajectory because, say, at different points, it can have different velocities, so it's not a problem. But can we have a trajectory like this? We cannot have this kind of trajectories in phase space, where the force on the particle, if it is not time dependent, okay? Because you see, if a particle is in this state with this position and this velocity, what it seems is that it can go either in this way or in this way, right? As I have drawn the trajectory like this. So it is not specified what the future will be if we have a particle with this state for this kind of trajectories. Now, can we have a closed loop in this trajectory? That is, the position and velocity are changing, but it is coming back to the same state again and again. Well, as you might have got it, actually we can have this. This is the trajectory of a kind of periodic motion. So for a periodic motion, we'll have a closed loop like this. These phase trajectories, we always have to specify a direction. That is, with increasing time, in which direction the points in this phase space will move. That is it like this, okay, or like this? So by these directions, we represent that with increasing time, the position and velocities will increase like this, in this direction. Now, we were considering a one particle system here, okay? The position and velocity of that particle we specified in this space, and then we traced what position and velocities it will attain through the course of its journey, right? So for that one particle, it may seem that this phase space should be just two-dimensional. One dimension will contain the position and the other dimension will contain the velocity. But actually, it is not two-dimensional. Because in reality, we know that the position is a vector, right? It can have three components, x, y, and z. And the velocity is a vector quantity too. So it can have three independent components as well. Now, in order to describe the motion of a particle in three dimensions, as you saw, we need six-dimensional phase space. 3 dimensions of position and 3 dimensions of velocity or momentum. If we have two particles, well, then we need 12 dimensions of phase space, right? And if the room is filled with a number of gas particles, which is of the order of Avogadro's number, you can imagine what the number of the dimension of the phase space should be in order to describe that system. But no matter what the dimension of the phase space is, the system will have a trajectory in those phase space, and that trajectory is always a curve in that phase space. For our case here, we are considering an one-dimensional oscillator, okay? So the motion is along one dimension. So the position has only one component, that is maybe we can call it x component, and the velocity has only one component too, right? So for our problem, the phase space will be two-dimensional. We can call this phase space a phase plane. Now let's find out what a phase space trajectory for a simple harmonic oscillator would look like. And this is our simple harmonic oscillator, and let's draw the phase space diagram for this simple harmonic oscillator. So along the horizontal axis, we consider the position of this oscillator, let's call that x, and along the vertical axis, we consider the velocity of that oscillator. So let's denote that with x dot, time derivative of the position. It's equal to velocity, right? Now let's find out the position of this oscillator with respect to some point. So as you can see, this is the position when it reaches this point, right? And maybe this is the position, so this one, yeah, this one is when it goes back in this direction, and this should be its equilibrium position, right? So if we measure the position with respect to this equilibrium point, you can see we can say that the direction this way is negative and the direction this way is positive. You can say so, right? It doesn't matter. So you can say that when this oscillator reaches this point, okay, it stops for a moment, right? So the velocity is 0 here. So at maximum distance here, the velocity is 0, right? So if this direction is positive, so we can find out that point here maybe, okay? And for that, the velocity is 0. So you can say that the phase space point should be here, okay? Corresponding to this state of the oscillator, it should locate here, right? Alright, what about at this point? Well, again, you can see at this point the velocity is again 0, okay? But this point is minus the maximum distance, which we can say the amplitude too, right? So this is the negative amplitude, so you can say, okay, so this is that point, right? That minus amplitude, and the velocity is here again 0. So these 2 points corresponds to those 2 states of the oscillator. Okay, alright, and now at equilibrium position, where the position we consider to be 0, you can see that velocity is maximum here, because for simple harmonic motion at equilibrium position, the velocity is maximum, you know that, right? So at equilibrium position, x equals 0, the velocity is maximum. Maybe this is the maximum velocity. And as you can see that it can be positive too, and it can be negative too, right? This velocity. So this direction we are considering the positive direction, the downward direction. So when it comes here, when it's moving in this direction horizontally, we can say that the velocity is positive, which corresponds to this point. And when it is moving in this direction upward, we can say that the velocity is negative. That is, it corresponds to this point on the phase space. So these are the points that we could specify by visualizing this simple harmonic oscillation, right? Now, although these 4 points are not convincing enough to claim that the trajectory of the phase space for this simple harmonic motion should be an ellipse, but if you plot all the velocities and position here, you should actually get an ellipse. So maybe you should get an ellipse like this. Well, how do we get an ellipse? Well, we'll verify that a little later, okay? So for the moment, just believe me, okay? So this is an ellipse which is actually the trajectory in the phase space for the simple harmonic motion. But as I said earlier, the trajectory should have a direction. That is, if we have time increasing, what should be the direction of this trajectory? Okay, so from this diagram, as you can see, when the object is here, this point corresponds to this point in the phase space. So after that, it goes in the upward direction, and we said that, okay, the upward direction is negative, so its velocity and position, velocity becomes negative, still the position is not. So as you can see, its direction should be this way, right? So here the trajectory of the phase space, in the phase space, should be in this direction for this simple harmonic oscillator. Okay, now what if we started with a different initial condition? That is, maybe we started with an oscillator and extended it a little further. So that means at here at the maximum amplitude, the position would be something here, right? So that position would correspond to maybe this point, okay? So we extended it a little more, right? So the amplitude would increase, right? So if the amplitude is increased in this direction, you see it will go in that direction too. So the amplitude in this direction will also be equal to that amount, right? So that will correspond to this point in the phase space. And similarly, if you evaluate all the points, you will see that we'll get a trajectory like this, which will again be an ellipse, but you see it will be equidistant from that previous ellipse. Now what this means is that if you specify an initial condition, say this was our initial condition, okay, for this ellipse, right? And for the previous one, this was the initial condition. It actually gives you a unique trajectory in the phase space. So if you stretch it by this amount, it gives you this particular phase trajectory. Okay, so if you stretch from the initial position by this amount, it should give you this trajectory. So that means by specifying a position in the phase space, we can actually uniquely specify the phase space trajectory of that motion, right? Okay, so that means a point, if we just give you any point on the phase space and say, well, this is the point, this represents a state of that oscillating system, you can actually find out all the positions and velocities over the course of time that it will traverse. Okay, you can find out its trajectory, and you need to show the direction here too. Again, it will be in the same direction. Okay, now the collection of all these trajectories, we call that a phase portrait. That is, for different initial conditions, there will be different trajectories, and the collection of all the trajectories, we call it the phase portrait of that system. Now, as you should have already guessed, that these lines actually, which corresponds to different initial conditions, actually you can think of it as you're giving different amount of energy. So if you are stretching by this amount, you are giving a small energy, and for this amount a little higher energy, and for this amount you are giving some more higher energy, right? So what you can see here, you can think of this phase portrait thing, that for all the energies that you give to the system, it traverses different trajectories. Okay, let's find out why the phase space trajectory of a simple harmonic oscillator is an ellipse by using the energy of a simple harmonic oscillator. So what's the total energy of a simple harmonic oscillator? We know that the total energy is the sum of the kinetic energy plus the potential energy. Okay, so we can write down the kinetic energy to be equal to half mv squared, and the potential energy for a simple harmonic oscillator is half kx squared, where x is the displacement from the equilibrium position, right? So this is the total energy. Now let's just manipulate this equation a little in order to find out the shape of the phase space trajectory. So we plotted here the position and velocity. Okay, so if we consider here position and velocity to be two independent variables here, we can find out the shape of that trajectory from this equation. What to do? Well, as we can see that we can rewrite this equation like x squared over 2e over k. Well, how do we get this thing? Well, you have to just divide this quantity with E and rewrite this thing, right? You get this. So this thing plus V squared. Again, what you have here is 2 times this E divided by that mass. Again, we got this by using the same thing, dividing the whole thing with E and rewriting this quantity here will be equal to 1 as you divided the whole thing by E, right? So if you write this quantity as square root of this and then square it, you get the same thing, right? So let's write this as square root of that same thing and then square it. Okay, so let's do it here again. So what you see here is an equation which is very similar to x squared over a squared plus y squared over b squared equal to 1. And this equation is an equation of ellipse, right? So this is a trajectory which will look like an ellipse. That's why the phase space trajectory of a simple harmonic oscillator looks like an ellipse. Okay? Now, this quantity under x, we call this quantity square root of 2e over k, the semi-major axis here, which is A, and this from here you can see that if you specify the energy, okay, for the simple harmonic oscillator, you actually specify the A and B, right? That means you specify that ellipse. Okay, so by giving some extra energy to the system, you are changing this A and B. So that means you are going from one trajectory to another trajectory. Again, that would be an ellipse because of this form of the equation, right? So this family of ellipses is actually the phase space portrait of simple harmonic oscillation. So let's complete this diagram for now. So this is the phase portrait of a simple harmonic oscillator. Now, why this phase space is important? Well, as you can see that a particular motion represents a unique trajectory in this phase space. So if you can just specify a single point on this trajectory, you can actually find out that trajectory, right? By using this conservation of energy, right? So that means if you know that a simple harmonic oscillator at any given time, its motion or its state is represented by this point, well, then you can find out the trajectory that it will traverse throughout the course of time. Okay, so you will know all the possible positions and velocities of that motion. Now let us have a look at the phase space of a pendulum in real time. So let's say we released a pendulum from this point, okay, and we want to find out the phase space diagram for this motion. Now, as you can see here that in the horizontal axis we put angle, and in the vertical axis we put angular velocity. And well, previously we did with position and velocity, so it is just the angular version of the phase space. So it can be done, right? Okay, so let's say we have a pendulum like this, and we stretched it and released it from this position. So for this motion, we'll have a corresponding phase space diagram like this. Now, why so many diagrams? Well, this is due to the periodic nature of the angles, right? So from 0 to 2 pi, and then the angle repeats itself. So you can either consider that, or you can say, well, we'll consider different angles after 2 pi. So that's why we have so many points for single motion, right? Okay, so it doesn't matter actually for now. Okay, so let's concentrate on this phase space diagram only. So for this motion, you see, this is the phase space diagram, but previously you saw, well, this should look like an ellipse. Well, here the semi-major axis and minor axis maybe were very nearly equal, so that's why we have this circular type of shape. It doesn't matter, but the shape will be valid until the motion is simple harmonic. So if we release it from maybe a higher distance, well, then maybe the elliptic shape will not cover, right? So let's just increase it a little more like this. You see some angularity is here around this kind of position, right? So let's increase it a little more. You see that oval shape, but again that angular nature for this one, where we released it from a very high height, okay, like this. You see that the phase space diagram looks like this. And if you do it from even a little more, maybe, yeah, you release it from here, it covers this circular path. The phase space diagram is like this, which is not actually an ellipse, right? This angular shape is there. And if you do it like this, say you release it from this position and it goes like this and just a little more maybe, so that it crosses the whole that point again, right? So if you do that, what you see is it is not periodic, right? You see, it is not coming back. Now it is coming back, but a little earlier, what you saw is that line. From here, it went again like this. So for a pendulum, if it goes on a circle, like if you give it enough energy, it will go on a circle, and the phase space diagram would look like this.